So maybe we can start now, right? It's 11:35. Okay. Okay. So introduction for this today's speaker. So Dibya Sankar, well, his education qualifications. He did his BSc from Scottish Church and joined the integrated PhD program here in TIFR in 2017, and has been working in Professor Shandip Ghosh's lab, the optical spectroscopy lab. So am I right this far, Dibya Sankar?
Yeah.
Okay, so today he's gonna take us on a journey where he would describe some of his so-called failed experiments, but actually the insights he got from them, and how it has helped him like set on a proper course. So without much delay, I would like to hand over to Dibya Sankar to So it's all yours, Dibya Sankar.
Yeah. Thanks. I'm going to start sharing. Oh, wait a second. It's showing some. I have to grant some permission. It's showing I should grant some permission or something for sharing. Okay. I'm just leaving for 1 minute. I'm rejoining. Okay. Yeah. Can you hear me?
Yes, you are loud and clear. You are loud and clear.
Oh. Okay. And now tell me whether you can see my screen.
Yes, I can see your screen.
Yeah. Okay.
Okay.
Uh, so I'm starting my talk. So I just wanted to say one thing. That today is 5th June. This is World Environment Day, and probably you know this person by now because we have lost him few days back. And it's Sundarlal Bhoguna, who was a main person behind Chipko movement. So I will start. I would request everyone to start this meeting with 1 minute silence for Sundarlal Bhoguna and all other environmentalists who has given their lives for betterment of our environment. So anyway, okay, thanks. So now I will proceed with my talk. So, as you already know, the title of the talk is My Failed Experiments. Okay. And Somak has already give the introduction about me. I work with Professor Sandeep Bose in optical spectroscopy group in the CMP. So let's start with knowing what Professor Smith thinks. Okay. So I just leave this cartoon strip for a while and just go through it. What Professor Smith thinks about uh, who has not succeeded in their experiments. So yeah, people will say that failure is an integral part of the discovery process, and that you need to fail to know what doesn't work. Usually, people who fail, they say these things. So I am one of them. So today I'm going to convince you that why that failure of my experiment was integral part of the discovery process, and whatever what I have learned from this process, these things. Okay. So if you just ask me whether it was completely failed, really, I would say that no, I didn't get any publishable result out of those experiments. Okay, but it's okay as long as I have learned something out of it. So I can say that I can handle some instruments. I have gained some expertise to handle some instruments while I was doing this. Now it seems that failed experiments, but I have learned something through that process. So the classic example, obviously, Edison's example, that he told that I have not failed 10,000 times, that I have just shown that these 10,000 ways bulb cannot be made. Okay, so important is here, say after 1 to do some experiment in this way can just go through it, and they can understand that the in this process this work cannot be done. So that's why negative results also should give the equal importance as a positive ones. So with these positive vibes, I'm going to present this in my presentation. So now what kind of experiments I do in my lab? I do optical spectroscopy of 2D semiconductors. Now, if I just leave with this line, you will probably nod your head, pata hai, but probably some of you can have some problem getting it what actually I do. So wait, I will explain word by word. So the optical is related to optics, which means light. So I deal with light, and in our lab we have a amplifier, that is the total optical range we can use to do our experiment. And the word spectroscopy is very general, which means the response over a large wavelength range. So you have already heard a talk on photo emission spectroscopy and electron spectroscopy, probably. Uh, but what does that word spectroscopy mean? Spectroscopy means, even in the photo emission spectroscopy, the tool they use is a photoelectron, but the experiment they do that you shine a fixed energy photoelectron on your sample, on your system, and you want to see how that system responses for a large wavelength range, and that is called spectroscopy. So I do spectroscopy using light, visible, optical means. And the word 2D like graphene. That's all. But it has some difference, obviously. For graphene, it's only the carbon atom, but the kind of material we deal with is called transition metal dichalcogenides, where we have one transition metal atom and two chalcogenide atom. So material-wise, element-wise, it is different, and structurally it has some different, but it has very, close resemblance with graphene. So it has hexagonal structure, it is layered structure, and two layers are adjacent layers are attached to van der Waals attraction, so you can peel off like graphene. So this is the material I work with, and the most important part, which is different than graphene is their semiconductor. Okay, so I think everyone knows what semiconductor is, and if you see that semiconductor band gap is order of EV energy. Okay, and what corresponds to order of EV energy is optical spectrum. So light is actually a very good tool to study physics around this band gap. So if I summarize, so I study band edge property of 2D semiconductor using optics. That is optical spectroscopy of 2D semiconductors. Okay. So then what kind of experiments I do? This is the total list, or maybe not total, but some of the experiments which we can do in our lab. Though my PhD is kind of concentrated on these three experiments till now, I don't know where it will go. But today I will concentrate on very small part of it is ellipsometry, and whatever experiment I did in ellipsometry, I'll discuss that. And before going to theory, before going to experiment, let's discuss some theory. And the first question I will ask, what is Fresnel equation? And any two of you at least should answer this question. But the challenge is you have to say it in one line, in a very simple language, in one line. So please, any two of you volunteer what you understand by Fresnel equation. No, I mean, if you don't volunteer, then this is the end of the talk. I'm not going to proceed. Okay. So please volunteer, at least one of you. No. What do you understand? What do you understand by Fresnel equation? You have read it obviously in your BSc, in your MSc. No. Fresnel's equation. No, it's not related to diffraction. Guys should.
Is it related to polarization? Like
Yes. Go ahead. What do you remember?
P polarization and S polarization. There were two equations for that.
What equation? That's what I'm trying to say. There was P polarization, S polarization, but how they're different?
I think in terms of their some combination of impedance, like the material impedance that has. I don't remember the exact equation. Some
hey,
of the terms.
You people are doing ED2. ED2 has this syllabus.
Yeah, but I don't remember it exactly.
Okay, so anyone else remember?
Yeah, so
go ahead.
Fresnel equation describes the reflection or transmission at any material surface.
And
so
Snell's law also describes the refraction subsurface.
Yes, right. So I think Fresnel equation is more generalized. Snell can be derived from Fresnel.
Not really. So what the other guy told, I don't remember. Yeah. Right. Yeah. So how will generally describe that phenomena, that one component going down, another component is up? How will generally say?
Conservation of energy.
No.
Sorry, Dibya, could you just reframe your question? Like you're asking, like, what is the phenomena of the one component going down or something like that?
No. What I'm asking, what you understand by Fresnel equation? Describe me in a normal, simple language in one line.
I mean, okay, so it can be like the ratio of the electric field of the reflected and the transmitted wave, like when light beam is incident on the boundary of a medium.
Right.
Yeah, I mean, that's what I could conjure up from my last 2 years learning. So there are many
Okay. So it seems we have forgotten. Okay. What is Fresnel equation? We have forgotten that. Uh, anyway, let's proceed. So my understanding about what is Fresnel equation, that reflectance or reflectivity at any surface, I mean at any interface, that depends on polarization of the electromagnetic wave. Now you remember what the guy was trying to say. Uh, what was his name? Shikhar, probably. What he was trying to say, that for two polarization, for S polarization and P polarization, the reflectivity curve is different for each interface. Okay. So if I show you the curve, this is the reflectivity and transmittivity curve to air to glass interface. There you see this RS RP is complementary to TSP, the transmission and reflectivity, basically. So you see for except 0° and 90°, the reflectivity curve for S polarization and P polarization are nowhere, same. So they are completely different for all angle of incidence except 0 and 90°. So probably now you remember that the Brewster angle is that specific angle where the RP, the reflectivity for P polarization, goes to 0. So if you shine an unpolarized light at that angle, the output light will be S polarized only. The P polarization will be completely clean. Okay, so now the language we understand better is a mathematical language. So this RS and RP is this coefficient of reflectivity. So not it's a reflection coefficient, not reflectivity. So the reflection coefficient can be written like this, where these NIs are complex numbers, and you probably know that the real part of the refractive index is refractive index, what we say, and the complex part of the refractive index is basically absorption. And for any real material, there is some absorption. So in general, these NIs are complex numbers. So now keeping that in mind, that NIs are complex number, I can always write this complex reflection coefficient like this, okay, in polar form. Okay, so for this is the RP tilde is complex reflection coefficient, and the RP is the amplitude, and theta p is the phase. Okay. So now
Dibya Sankar, I am sorry, I just want to just to interrupt you. Since you asked the question, I just want to hear you from take on that the equation you have showing you that one can find in the Wikipedia, and that is for the non-magnetic material. So I would like to hear from you what will be the equation if you have a magnetic materials.
I'm talking about only I'm talking about so throughout that my talk it's about dielectric.
Yeah, understand, but that should be okay. But what should be the equation of the Fresnel equation if you have a magnetic material? If one can say the one line.
Uh, Obviously, it will be deviated from. You should have some. The curve will be deviated, and you should have some say p component also for Brewster's angle. So the magnetic material will contribute to the reflectivity, the reflection coefficient for that, right?
So how I can understand it physically?
But it is bound physically.
What will be the involved in?
Because we have to satisfy.
But what will be the material property will? No. What will be the material property will come into the play, because non-magnetic material I just only worried about for the reflection coefficient. That's all you have put in it. But for the magnetic material, which property will come to a play in that case? And that will give you a deviation and all those things. Means I would like to say all those things is that what will be the highlight of the above of the textbooks chapter or the textbook you have raised the question that one can find the answer from the research. It's obviously that it is not written in the textbook.
Yeah. What you're trying to say is, I agree with you. Often I don't know that for magnetic material how, the equations will vary, or the Fresnel equation will be vary for magnetic. So I can, with intuition, I can say that they will be definitely different because the boundary condition will be different for those material. But I don't know exactly how they will vary. Yeah.
Hello.
Yeah.
Hi everyone. I think that mu will come into the play. That mu, if there is magnetic material,
Yeah,
then
but how
Exactly.
how they will
Exactly, but the question is definitely the that magnetic material, only the property is the susceptibility, which will definitely come. But the
magnetic
question
susceptibility.
that that Dibya Sankar is highlighted, that is what I'm asking, so that the juniors can get answer from that ongoing research, that if anyone or if it is in presence of his knowledge, that is might be it is very difficult. But the point is that how the new will change means, if I plot this two curve, what is the Dibya Sankar was showing for the non-magnetic material, if someone can perform like a simulation kind of a thing or whatever, because he is an expertise in that case. So I just would like to
So
answer
I think
that.
I can answer it.
Yeah, sure, go ahead.
So this n value, this reflective index, it's actually directly proportional to root of mu and epsilon, where epsilon is
Okay.
electrical permittivity, I guess, and the mu is the magnetic susceptibility. No, not susceptibility, permittivity actually. So if the mu is responding as a function of, so in normal electric material like which are non-magnetic, in those cases this mu is just mu naught. So the n basically depends on root of epsilon. Okay. Now, if you have a magnetic material, that mu will also give some response. Usually, the response of mu is very weak, so that's why you don't see much. But if there is a huge response,
But
like mu is,
that is no. That is what are you saying is usually not weak for the non-magnetic material case or the
yeah.
weakly magnetic
So
material case. But
suppose
let's say
if
I
it
have
is
a
not weak,
ferromagnetic,
yeah.
I have an anti-ferromagnetic. That
So
is the
what I
response is
remember
huge.
is that in place of N1 and N2, there will be a general term, impedance term. Let's say Z. Then when RS will go to zero, when the total term will become zero. I remember that it's called impedance matching, something like this. So yeah, there will be like what is impedance divided by under root of epsilon by mu, like some kind of this. So RS will
Yeah,
become
that is a vacuum impedance.
yeah. Here, no.
Okay.
Yeah, but in material also, epsilon and mu value will change. So we will get impedance of the material. So in place of when we trying to find this angle where RS becomes zero, we will have to find the angle when this the total impedance matching. In general, we have to find out when this term will become zero. Where taking Z1 and Z2.
Yeah, Suraj, do you want to comment something?
Yeah, so Dibya Sankar, so I would like to just to say that if possible, just you can try a simulation on that if you have a fine time, and give a visual picture if you have a later on some that as an email. So I would like to hear on that a very good thing. That is because it is a beyond a textbook point, because you raise a very important question. And I guess if you can have this plot with a magnetic material, whatever was simplification you can take as a, let's say the first order simplification, where as Shobhik or tell that, let's say that the mu is obviously that is the first institution that mu is play a role, and that is modified your electromagnetic that wave which is the propagate through your material, and whatever be the change, and through that you can find this curve to curve, and you can post that later on in your mail or something.
Okay.
That is will be very interesting.
Right.
Sure, thank you.
Yeah. This is the way. I mean, I like that. Like, so they told this. So I never thought, because I don't deal with the ferromagnetic or magnetic materials. But yes, this is a good thing to actually explore. Okay. Okay. So here was I. So now I take a ratio. So RP tilde divided by RS tilde, and here you have an amplitude which is magnitude RP divided by magnitude RS, and phase which is theta p minus theta s. So now you can denote that as tan psi and e to the power I delta. Just you are saying RP by RS is tan psi, and theta p minus theta is delta. Now these two parameters, this tan psi and delta, are called ellipsometry parameters, and they are actually very rich parameters. You can extract several parameter value from if you just perform this experiment tan psi and delta, and if you have the tan psi and delta value, you can simulate back and get several properties of the material out of it. So like refractive index, definitely you can, the extinction coefficient you can, and the real imaginary part of the dielectric function that can be extracted. And the list goes on. And one most important thing that these parameter value and distance I and delta, they depend heavily on the thickness of the reflecting surface. So in semiconductor industry, they actually use this process to monitor the growth, the layer growth in situ while they are growing. So basically, they shine that laser and continuously monitor this tan psi and delta. So they have a simulated curve that when there is 5 nanometer thick SiO2 on Si substrate, then the spectrum will look like this. So they stop their growth at that point. So this is a very well-known technique in semiconductor industry. And so I think we are armed with enough theory. I assume that. So keeping that in mind, let's jump into the experiment. And the experiment said, yeah, yeah. Okay, yeah. Extinction coefficient is basically the imaginary part of the refractive index, what I mentioned. Like n is a complex quantity, n plus ik. That k is the extinction coefficient, which actually give rise to absorption in materials. Okay.
And one small question, Dibya. So can you please explain those subscript R, P, R, S?
The small rp is
that
rp
subscript.
tilde.
P stand for?
P polarization and S is the P polarization and S polarization. P and S are some German term. So the S polarization is polarization which is perpendicular to the reflection plane, and P polarization is which is parallel to the.
Can you explain that thing little?
Okay, so can you see me? The video?
Okay.
Yeah. So say
Yes, I
the
understand.
the reflecting surface is like this, and you can have two polarizations. Say you're linearly polarized in this way. So on the surface, you see the vibrations are in plane, out of plane, like this. So they are perpendicular to the surface. So that is called S polarization. And if you have a linear polarization like this, so it will fall on the surface like this. So this is parallel to the reflecting surface. That is called P polarization.
Okay, thanks.
Okay. And Fresnel equation says that these two reflection coefficient for these two polarization are different. Okay. So the experiment setup is very simple. That just neglect those optional things, the compensator in between. They're optional. It's written. The setup is very simple. You have light source. You have a polarizer. So basically, you are shining a polarized light on your sample at some arbitrary angle phi, and you are detecting that reflected light through an analyzer, detecting that light is detected through an analyzer. Okay, this is a simple setup to do ellipsometry. And now it can easily be shown that you need to do 3 measurements to know ellipsometry parameters. And I think everyone understood which 3 experiments you should do, right? Everyone understood? What 3 experiments you will do to know the ellipsometry parameters? Anyone? No one? Can you guess which experiments?
It's a reflection and transmission.
No. There is no question of transmission. This is always ellipsometry is a reflecting mode.
Yeah, reflection geometry.
Yeah. So when someone says like this, you can it can easily be shown the 3 measurement can give you ellipsometry parameter. You should say like this that whatever we have thought is wrong. So just show us what 3 experiments you will do to extract out ellipsometry parameters. Okay. So for that, I will take a little diversion to say you something about Jones matrix formalism. Okay. The Jones matrix formalism is very simple thing. So you understand if you have a plane polarized light, okay, so the direction of the propagation of the wave is say z direction. Then the electric field can only be in either x or y. So it's basically a 2D plane where the electric field can be. And any vector on the 2D plane can be denoted by a column vector. Okay, the 2 cross 1 column vector will define any state of polarization. So all this polarized light state can be denoted as a 2 cross 1 column matrix. And when that light is passing through some optical element, so the polarization will be modulated in some way. So you have a vector at the output path and a vector in the input path, and how they are related. For that, you need a 2 cross 2 matrix. So for all optical elements, you can denote that optical element by a 2 cross 2 matrix, which relates the output polarization to the input polarization. Those 2 cross 2 matrix is called Jones matrix. Okay. So now a quick question: what is a Jones matrix for a lens? Someone please volunteer. What is a Jones matrix? So whatever I told, by knowing that, what should be the Jones matrix for a lens? So you understand that you have output light which has a state of polarization, and you have input light which is another state of polarization. Then how they are related is denoted by a 2 cross 2 matrix, and that matrix is called Jones matrix. So say you are launching a polarized light on a simple lens, so ideal simple lens. So you are launching a polarized light, and some polarized light is going out. Now my question is how these polarization are related, or in other words, how the polarization will be, changed by going through a lens. That is the Jones matrix for lens.
Identity matrix?
Yeah, identity matrix. Who told that? Ram, right? Yeah. So I think you have understood then. This is an identity matrix because a lens should not affect the state of polarization. So whatever polarization you are launching, the output polarization will be same. So for lens, this should be a identity matrix. But it will obviously not be for different materials which actually modulate the state of polarization. So just leave you a question with you that what is the Jones matrix for quarter wave plate whose fast axis at 45 degree to the horizontal. Just you can search over internet, or you can just work out how they will change. So knowing that all optical elements correspond to some matrix, 2 cross 2 matrix, let's go to a simulation. So one thing I should mention that using Jones matrix, just think about it. You cannot denote an unpolarized light. Okay, it has to be polarized. That then only you can denote it by a column vector. Okay, so to denote unpolarized light, you should go another level up, which is called Muller matrix. Using Muller matrix, you can describe unpolarized light, and that is a 4 cross 4 matrix and 4 cross 1 column vector. But here, we're in a simple case, Jones matrix, you are dealing with only polarized light. So it states that initial state after passing through a linear polarizer at theta degree is denoted by this vector. Okay. So this is basically unpolarized light passing through a polarizer at theta degree. Then the Jones matrix for a polarizer at any alpha degree angle with respect to horizontal axis is denoted by this matrix, and the sample matrix is denoted like this. Okay, and these A and B are basically A is basically the optical setup is like this, that the incident polarization is at 45 degree, the sample at any arbitrary angle, then the analyzer at 90 degree. So if I write it down, this is initial polarization at 45 degree, then sample at any arbitrary angle, then analyzer at pi by 2. So this is the vector, and if you want to get the intensity, you have to take mod square. The intensity will be this. And EL squared is basically EL squared by 2. This is basically the I naught for my experiment, which is basically sustained response. So light passing through different elements. So obviously their intensity is going to change. Okay. So how the intensity is changed, that is captured in this parameter I naught. So you see there is, even if there is a sample inside, there is no A or B parameter here. Okay. This is only I naught. Then you do another measurement where the rest of the setup is same. Incident polarization 45 degrees, sample at any arbitrary angle, but the analyzer intensity is this. So now you divide the second expression by the first expression, the EL square by 2 will be cancelled out. So you can extract A, which is tan psi basically, from this by performing these two experiments. Now you do another experiment where the setup is undisturbed, but the analyzer at a 45 degree angle. Okay. So you again calculate this is the vector and this is the final intensity. Again, you divide this by the first expression. So EL square by 2 will be gone. And by now you know A. So knowing A, you can get B. So you see, you have two parameters, tan psi and delta, but for that you need to do three experiments because you want to, you have to normalize it. You have to cancel the system response. So you should know that I naught, this EL squared by 2 for that. Okay. So by performing these three experiments, one analyzer kept at 90 degree, analyzer kept at 0 degree, analyzer kept at 45 degree, you can extract three ellipsometry parameters. Okay. But there is a catch. There is but. So you can do that measurement. You can do three measurement and you know the ellipsometry parameter. But this is a DC measurement. And what I mean by DC measurement, I have a constant source of light. And a polarizer, the polarized light is also a constant source, and I am measuring. I am detecting that light as a constant source. So what's the problem with that? Because as you are measuring as a constant background, so suppose you switch on your lab light and that will be catch in your detector and your signal will be, disturbed. Suppose your phone and screen light will go to detector and it will disturb the signal. So it depends on the absolute background value if you do a DC measurement. And that's why this inherent noise in all DC measurements are much more. So, and again, if you, like I have shown you have to do algebraic manipulation, like you have to divide, you have to subtract, like that. So those algebraic manipulation will increase the noise in it. So I have to do some AC measurement to minimize my noise in my experiment. Now you will definitely ask what is AC measurement, right? But I will answer by quoting a poem by Rabindranath Tagore. Yeah.
So can you go back to the previous slide?
Sorry. Yeah.
Can you repeat once more? So what are the three experiment that you will perform? So looking at the diagram that you showed here, like what are the relative angles that you showed in the your mathematical files? So
yeah. So I have light source. There's unpolarized light coming from the light source. Then the polarizer is at 45 degree angle. At that 45 is basically with the horizontal. Okay. So say that direction of propagation is like this, and your polarization is 45 to this. Okay. Then it is falling on a sample, and this angle, it is denoted by phi there. That angle may be arbitrary, anything.
okay.
And then you are detecting through an analyzer. Again, the analyzer angle can be varied.
Right.
And then the polarized light you are detecting in the detector.
Right.
So I am basically doing the experiment by varying the analyzer angle. So once I am doing the experiment with analyzer angle 0 degree, then I am doing analyzer at 90 degree, and then analyzer at 45 degree.
I see. And you measured the absolute intensity in the detector?
Yeah. For this case, yes, I am measuring the absolute intensity. So basically, it's a DC measurement. Yeah.
Okay. Yeah. Thanks.
Yeah. So what I was telling that if you ask me what is AC measurement, so I will leave you a few lines by Rabindranath Tagore that not here, somewhere else, some other time. Okay. So this is beyond the scope of this talk. Someone maybe from our department can give a talk specifically on AC measurement, which is very integral part in all our experiments in condensed matter. So, but I will just leave you few catches That is that what is an AC measurement actually? That say I want to measure a parameter B, and you know that if you the parameter B is directly affected by parameter A. You know that. Okay. So now you disturb that parameter A periodically with a known frequency and a known phase, and you see how the parameter B is changing at that frequency, not only that, at that phase. Okay, this is called an AC measurement, because it can happen that you are doing a measurement at 60 hertz and probably there is some light in your lab which is blinking at 60 hertz. It may happen, but it is rare of the rarest that the phase of what you are modulating and that light will match. That is rare of the rarest. So usually what we do, that we use an instrument called lock-in amplifier, where we say to the instrument that, see, I am disturbing a parameter at 175 hertz and my phase is this. Now you measure the signal, what you are seeing, only at 175 hertz and only at that phase, okay, and show me that. So one direct advantage is that the signal to noise ratio increases drastically. The few order of magnitude you can improve there in signal to noise ratio. Okay, so now now the question is, okay, I have to modulate something, but what to modulate? So for any polarization sensitive measurement, one thing is to modulate periodically is the polarization of the light itself. But the question is, how will modulate a state of polarization of light? This is simple. I mean, you should know that that if you have a polarized light and if you pass through a retarder, say quarter wave plate or half wave plate like that, the state of polarization will be changed. Okay. So now you change the retardation of the retarder. I mean, modulate that, and as a result, the state of the polarization, the output polarization will be modulated. Now, what device? I mean, how we will modulate the retardation of a retarder? There are, number of devices available where you can do it. So, device I used is something called liquid crystal variable retarder, or LCVR. Okay. The device is simple. The structure is something like this: that you have a thin layer of liquid crystal in between two ITO coated glass substrate. And through that ITO coated glass substrate, you apply voltage. And as you apply voltage, the orientation of the liquid crystal is changed. And by that, you introduce anisotropy. And, anisotropy means you are applying different retardation for different voltage. Okay. So if you shine a light at 45 degree and you are modulating the voltage, so the liquid crystal is changing their orientation periodically, and the output polarization from the device will be modulated in such a way whatever voltage you are applying. Okay. So say if you are giving a square pulse like this, then you will as an output polarization, you will get a series of linearly polarized circular, linear circular like this. The modulation will be like this. So now the question is that you understood that retardation changes depending upon whatever voltage you are applying. Okay, and also the retardation curve changes with wavelength. So you know that what element, the element which is quarter wave plate for say 550 nanometer is not a quarter wave plate for 650 nanometer. Okay, so with wavelength you have to change something to compensate that. So that's why you have to calibrate your device. So, and I have also calibrated my device. So if you see closely what I'm doing, I'm changing the voltage in the x-axis. I'm applying different voltage. I'm measuring what is the retardance. And in our case, you see for we have several limitations. Like at 0 volt, at max you can go say 0.7 for 550 nanometer and 0.5 for 700 nanometers. That's the maximum retardance you can get. And as you apply voltage, it goes down. And I have shown here till 7, but I have done the experiment till 12 or something, 12, 13. But till that voltage also, that curve actually, at most reaches to say 0.1 or 0.08, something like that. So effectively, you cannot get a zero retardance, whatever large voltage you apply. So, but giving that, I mean, knowing that this is our retardation range, so we thought of something that we can perform experiment with this as well. So what we did, now you understood that the retardance profile is like this. It's almost a square wave. Okay, but how will analyze that signal? What is your model to analyze this? So my model is this. So my optical setup is here. You see this capital A, capital S, ret, and capital P. They are actually the Jones matrix for analyzer, sample, retarder, and polarizer, respectively. Okay. So my optical setup is polarizer at 0 degree, then retarder at plus 45 degree, then my sample, then analyzer at minus 45 degree. Now I'm saying that I will model this system discretely. Okay. When the retardation, when I'm applying say V1 voltage, I know the retardation is delta 1. So with that retardation, what is the resultant electric field? That is denoted by E delta 1. And for other case, when I'm applying voltage V2, the retardance is delta 2, and the resultant electric field is E D2. And if you just take mod square of that, you will get intensity. Now you have transformed this retardance curve to intensity curve. Now you have a square wave profile of intensity. And using Fourier analysis, you can say what is the DC term if you have a square wave with level this, and what is the first harmonic term for that. So I have calculated those. And again, to normalize, to get rid of that I naught parameter, I have to divide. So I have taken F by DC, and this is the final expression. But you see, there is two parameters I should extract, like tan, psi, and delta, but I have only one equation. So initially, we thought that, okay, we'll go ahead with this, because we'll perform the experiment with dielectric mirrors, like silicon mirrors. And for that, this delta parameter almost in our wavelength interest, the parameter almost tend to 180 degrees. So you can neglect that, and you can find the parameters iteratively. So you find tan psi and then come back and estimate delta like that. But then I suddenly discovered that, well, this was my optical setup. My analyzer was at minus 45 degree. So if I change the analyzer at plus 45 degree and I do two measurements, okay, then if I calculate the F by DC, same term, I get two independent, linearly independent equations. And from there, you can exactly solve tan psi and delta. So, okay, I will perform two experiments and I will exactly find tan psi and delta. So, with all this keeping in mind, I performed the experiment. And this is the curve we got. The top one is actually for the F by DC signal for analyzer at minus 45 degree, and the bottom one is analyzer at plus 45 degree. And if you use those F by DC expression and want to calculate the ultimate ellipsometry parameters, which look like this. Okay, the top one is tan psi and the bottom one is delta. This is for silicon mirror at 45 degree angle. Now, how it should look like. So this is the experiment which is done by one of my senior in lab. So for the same condition, silicon mirror at 45 degree angle, the curve should look like this. So there is no resemblance. Okay, it should be a flat curve. It should go down with wavelength. There should not be any oscillations in the signal. But we are measuring something this. The first question comes in mind is that obviously it may be the system response of the liquid crystal device itself. So I will do again two measurements. So two to get two parameters, and other two measurement, what is with sample, without sample. And I subtract those signals. So with sample minus without sample. Okay. So if I do that, you see the topmost curve is with sample, the middle one is without sample, and the difference between them is the lowest one. This is for analyzer at minus 45 degree, and if you do the same measurement with analyzer at plus 45 degree, you will see you will get this signal. Just to show you side by side, these are the two signals: the left one for minus 45 and the right one plus 45 degree. So you see the oscillations are still there, and if you take the final curves, like the difference and perform and calculate the tan psi and delta parameters, you see again these oscillations are there, and also the values are quite off. So we're stuck from where these spurious oscillations are coming. The first possibility we think of, that probably the fast axis of the liquid crystal variable retarder is actually changing with applied voltage. But why we suspected that? Because you can very firmly define the slow axis, because the liquid, when zero voltage, liquid crystals are all aligned in some fashion. So that axis is slow axis. But as you are applying voltage, you are changing their orientation. Okay, and not all of them are changing their orientation. The liquid crystal which is close to the glass substrate will not change that much, which is in between, somewhere in middle. So how can you define fast axis there in the instrument? So we thought probably you cannot define fast axis, and also the company marks the slow axis on the device, not the fast axis. So usually they mark the fast axis for quarter wave plate. They will mark the fast axis is this one. But for this device, they marked slow axis. And that is very firmly defined. So we thought probably that fast axis is changing with applied voltage. So we did the experiment, and we found that no, it's not actually changing. So our analyzer angle resolution is 2 degree, and up to the 2 degree variation, you cannot see any change. So basically, the fast axis is actually the perpendicular to the marked slow axis, which we assumed initially. Now our whole concentration went to these oscillations. Why these oscillations are coming? So we start to study the pattern of the oscillation. Is there any pattern? How much voltage am I applying? Is there any pattern that is shifting in this direction or that direction? So we performed this oscillation experiment. This is a transmission curve, only a transmission curve. Okay. So I have a linear polarized light. I don't remember what was the angle. No, it should be 45 degree. Yeah, it should be 45 degree. So I'm launching a polarized light at 45 degree, and I have a liquid crystal at 0 degree. And I forgot the analyzer angle. So for some analyzer angle, you are detecting the signal. Okay. And I do a complete transmission. So sample is nowhere in the picture. Just the liquid crystal and polarized light coming, polarized light out. So I did the experiment for several modulation voltage. So you see the red curve is showing for the modulation in between 0.2 and 0.45. The black curve shows I have shifted that modulation by 0.05. So now the modulation is 0.25 and 0.5, this kind of modulation. So I keep changing different keep trying different modulation and see how the oscillations are changing. So initially I could not see any pattern in it. So how your applied voltage is changing, has some effect on this oscillation. But one thing I noticed that you see that repetition pattern, the period of that oscillation is increasing with wavelength. And now, so for any optical spectroscopy people, this is a very common feature that this is the feature for interference oscillations. So they increase with increase in wavelength. So then we thought, okay, there may be some interference happening in that device. So we looked back to the transmission card provided by the company. And it's not like that before starting the experiment, we didn't look at it. We looked at it. But in our wavelength interest from 550 to 700 nanometer, the total change in the transmission is order of say 2% or 3%. And the interference oscillations, they're order of 1%. So initially we thought it is not going to affect. Okay. So we go on with that. But if I just show you side by side, this is the effective range we are working with, and the right side, the curve we have. And now if you just compare peak by peak and dip by dip, you will see there is some correlation between these two. Not exactly match, but some correlation in between. Now we look back to the transmission spectrum again, and we thought, okay, this is transmission spectrum, but at what applied voltage? So in principle, the company should not give me the applied voltage, okay? So they are just saying that if you don't apply any voltage, this is your transmission. So in this way, your intensity will be modulated for different wavelength. They have given that. But I am saying that whenever I'm modulating those liquid crystal, I am picking up some oscillation which is related to the interference. So then we questioned what is, I mean, this transmission measurement is measured at what voltage? Is that so that this transmission curve actually changes with applied voltage? So say you are applying 1 volt, the transmission curve is this. If you apply 12 volt, the transmission curve will shifted right, will be shifted left, or the period of the oscillation will be different. What is the how they're changing for a different applied voltage? Now, if that is the case, that the transmission curve actually changes with applied voltage, then there is a problem. That not only the output polarization coming from the device is changing, but at the same time, the intensity of that light is changing for each wavelength for all modulations. And the most important part is at that frequency, at that phase. Okay. So your not only the polarization, but intensity is also being modulated, which you don't want. So we know that in AC measurement, we actually, AC measurement, they are very sensitive to these very small changes in intensity. So definitely, if there is a fluctuations in intensity, you're going to pick that up uh, as some oscillating signal in your spectrum. So this is still the question. So at that time, I get rid of that. I packed up my devices and all. Then I realized that it may happen that this is the cause. So I have not verified this till now, that whether with applied voltage the transmission curve actually changes. So I'm doing something different. So after that, I have some plan to go back to the device and just measurement the transmission spectrum and understand and just see that whether the transmission spectrum is changing with applied voltage or not. So what is the remedy? The thing is, we don't have any solution till now. But we can say probably it may happen that the devices the company now selling, they are, so our device is 7, 8 years old. Okay, so now they have some advanced liquid crystal retarder and all. So probably this problem will not be there, but we don't know. But we saw that same kind of transmission oscillation, there's oscillation in the transmission spectrum in for the current devices as well. But for current devices, you have a very longer range of retardance. So you can apply +1 retardance to -1 retardance, including 0. So they are superior device. So probably this problem is not there for other devices. But we could not figure it out. And our conclusion is that this device is not good to do spectroscopic measurement, but it should work absolutely fine with lasers with a very specific wavelength and as a polarization switch. So people use this device as that. So they just someone need this kind of measurement that as a probe pulse you need a circular polarization, like for other cases you need linear, but as a probe you need circular. So basically you're allowing linear, change the circular, then linear. So for this switching process, this device should work fine for laser. Okay, so this is my end of the presentation. I finally will leave you with a poem by C.P. Kevapi, which says that keep Ithaca always in your mind, arriving there is what you are destined for, but don't hurry the journey at all, better if it lasts for years. So anyway, we have to do experiments, but we're not in hurry. We'll learn something in the process. And Ithaca gave you the marvelous journey. Without her, you wouldn't have set out. So I've learned these things only after I ventured to do this experiment. Otherwise, probably I could not have gained this experience. And if you find her poor, Ithaca won't have fooled you. Wise as you will have become, so full of experience, you will have understood by then what these Ithacas mean. So it may have unsuccessful experiments, but obviously you are wise and you are full of experience to understand that no, this experiment is not failed. I have learned something out of it. Okay, so I will leave you with another comic strip. This is the end of my almost 1 hour presentation. And if you have any question, you can ask, but I will not entertain this kind of questions. And only the question about the content. And if you wonder, was there any content? I would say yes, there was. And thanks for your attention.
Yeah, okay. So, Dibya Sankar, thanks a lot for this enthralling talk. So, it was a very nice presentation. Probably could have, cut down 5 or 6 minutes, just making a critical comment here. But other than that, it was a very nice talk.
Right.
So, and now the floor is open for questions. And if you guys have any, you can ask directly to Dibya Sankar after unmuting yourselves.
I have one.
Yeah.
So, so have you used some other means by for modulation of polarization other than this liquid crystal kind of thing?
Yeah. There is a very standard device researcher use worldwide. So that is called photoelastic modulator,
Right.
and probably you have also have that. So with PM you can do all this measurement. So I have done ellipsometry with that PM also. So initially, what was the actual motivation behind doing this experiment? So we thought if we can do the same measurement with some another device, liquid crystal, and there are some advantages I can say you over PM. The PM is a very high frequency operating device. Okay, 42 kilohertz in that frequency. So for our case at least, so if I say that 42 kilohertz very high frequency, Shupriyoda or you will say no, it's not very high. We work with gigahertz. Yeah, that's true. But for our lab at least, we work with say order of 100 hertz. So 170 hertz, 200 hertz, like that. So our device, all the devices are, I mean, responsive at that frequency range. So for us to measuring 42 kilohertz, 84 kilohertz is difficult. So we thought if we could do this experiment with liquid crystal, then we can do at low frequencies. So so if we could do that, probably we could explore what the other advantages over PM. But anyway, we failed.
But so you did not. So you could not able to see any response from your device with using PM or what?
No, I've done ellipsometry with PM. That works fine.
And that works fine.
Yeah, excellent.
Okay.
We're just exploring another device. So can we do the same experiment with the other device?
Right. Okay.
Okay. Dibya, it is a nice talk. So probably that the first time I am hearing a one talk where speaker itself has bound that era of question. That is an interesting fact with that note that it is a one talk, I must say, but with a lot of failure laser. I still remember the one of the keynotes given by the Philip Kim that the thesis should be full of a failure experimental result rather than a successful result. A successful result should be a last topic of your thesis. Anyway, so coming, I have just that one technical note or the technical just a question one part. So how fast this measurement can be done? This as you can showing that the AC kind of a pulse that you have going to the lambda by 4 to lambda by 2. This is a quarter to the half quarter. So how fast this switching is possible without any artifact?
Yeah, so I had two dedicated slides to describe that, but I then realized that talk will be 1.5 hours. So I let it on the listeners. So if anyone asks, I will answer that. So yes, there is problem. So the problem is that liquid crystal retarder, they are actually very what should I say, long response device, or in terms it's not fast responding device. Okay, so for one cycle, so when you are applying voltage from 0 to some V volt, it takes order of millisecond time to saturate actually in that level. So basically liquid crystals are, they're changing their orientation, right? This changing time is order of millisecond. So in principle, the device, the liquid crystal retarder can operate from 1 hertz to 200 hertz, 200 or 250 hertz. Okay. But we check that. So if I work with say 170 hertz or say 180 hertz, the output intensity curve will not be a square wave. It will be kind of trapezoidal. Not only trapezoidal, it will go like this, saturated element, then come back. It's go like this. So they will significantly deform from the square wave. So we have to work with very low frequency. So all these measurements are done in 25 hertz or 30 hertz, maybe 20 hertz, sorry, 20 hertz. So this is one thing that you have to work. Then again, these new devices which they are selling, the same company, they have the very fast response. You can do 120, 170 hertz measurement with that. Obviously, the measurement time will be longer as we're doing.
Yeah, so that means your integration time will be very large. So
right.
Yeah. Okay. Thank you.
So Dibya Sankar, I have a question. So the experiments that you showed, so are they done at room temperature or like you go down to like low?
Yeah, no. It's all the room.
Sorry, your voice is getting a bit cracked up. So there was some, I guess, net.
Oh, sorry, sir. No. They all room temperature measurement, no like low temperature.
Room temperature measurements. Okay. So okay, so I am deviating a bit from your slide. So I want to ask you like, but you do like low temperature measurements, right? Also, or yeah. So either you use liquid nitrogen or liquid helium to go down to the low temperature regimes, right? So one question I want to ask in that regard is that
we have I have some internet problems, so it has delayed.
Okay, but you can hear me clearly, right?
Yeah, go ahead. There is a lag.
Okay. So I wanted to ask. So when you pour in liquid nitrogen and liquid helium, it is constantly boiling. So I mean, and with that boiling comes in the vibrations. So in your experiments, does that? I mean, in your low temperature experiments, does that boiling and vibrations give rise to problems? And if so, how do you like isolate that? Like take care of that vibration part. I mean, this may appear as
for
yeah. Please go ahead.
No. For now, the liquid nitrogen setup we have, there is a homemade setup. Okay. So there you pour the liquid nitrogen, the sample stage goes through the liquid nitrogen temperature, and you remove the nitrogen source and do the measurement. So that is completely quiet. And the other setup now I use for low temperature is a pulsed, that is a closed cycle cryostat. So they have obviously very huge vibrations, but that should be okay if your sample is large enough and your spot is small, then it should fine, and your sample is uniform. This is fine. But the kind of sample I deal with, they are non-uniform, very small. So we have made an arrangement where actually you make a connection from your cold head to the sample stage. So sample stage is on your optical table, screwed well. There is no vibration on that. But you connect the cold head to the sample stage through a braided wire, copper wire. Okay. So if there is vibration, the copper wire will be moved like this. If there is low frequency vibration or any kind of vibration, but the heat will transmit from the cold head to sample. Obviously, there will be loss. So with that cryostat, you can go up to 4 Kelvin, 4.5 Kelvin maybe. But if you do this arrangement, the at most I can go now is 25 Kelvin. So we have to sacrifice in that part. And other device Vishwas use is this pulse tube puller. Their inherent noise is, low than the closed cycle cryostat. But again, he has done this same kind of arrangement. So he does the measurement where the vibrations are order of say 2 micron, 3 micron, like that. So if you have a say 5 micron, 7 micron, order of 10 micron sample, this should be fine.
Okay. So actually, in that regard, I would like to ask. So regarding the sample size, it's fine, but the signal that is like given off from your sample, so it undergoes attenuation, it undergoes phase shifts, right? So do you take into account? I mean, do you have any model describing the errors that you get and you incorporate them into your final result? So is there any error model that you follow? Any standard error model?
No. I don't know. I mean, what we're actually trying to say. I mean.
So what I'm trying to say is that the signal that you catch, okay, so that is, I mean, that traverses some distance from your sample, right? Your sample gives some signal and then you catch it in your analyzer. So the distance it travels, so the time it takes, in that time it undergoes some attenuations, or you have maybe, let's say, some imperfections in your the pathway, so it can, like, hit bends and get phase shifts. So
No,
those,
I don't have any oscillating device. All my setup element, optical elements, they're
right,
clumped on the optical table. Like my analyzer, sample, polarizer, detector, source, everything is clamped on my device. So what you're saying, that can, arise in one case. That is, no people. Initially, 50 years back, maybe, or maybe nowadays also. I did that in my, I tried that in my DP2, where I tried to do the same measurement by rotating a quarter wave plate. Okay.
okay,
So you can just think about it that a quarter wave plate has a fast axis, and if you mount it on some arrangement which will rotate at, say, 20 hertz or 30 hertz, and with that you can continuously modulate the state of output polarization. Okay. So in that case, you can say that probably this quarter wave plate should move like this only. But what if they're doing like this? So that will introduce noise. So the measurement I did with this rotating quarter wave plate, yes, I saw that this is very noisy. So this is not a perfect rotation in this plane, but there is some oscillation. So the beam is actually on the detector. The beam is going like this or going like this somewhere. So that will introduce noise. But for this case, everything is clamped on the cable. They are stable. So there is no relative movement between the optical elements. That's what I'm saying.
right, right. Actually, the point I was trying to make, so one aspect of it was that, so when you have some beam that is going through some medium, so it always undergoes attenuation, because like it goes falls off exponentially, e to the power minus lambda x, where lambda is the characteristic inverse characteristic length, right?
No,
So I
it
was
depends on absorption. So
right,
in
right,
air,
yeah,
absorption
So,
is
so
very
let
less
me
for.
just, Dibya, just let me just rephrase what is this question Shomok is trying to asking you. Is like a AC loss in a through a wire. He is basically trying to asking. Okay,
Oh,
for
no,
your
no,
case, it is very low. What is very clearly
very low.
understood, Shomok. He is working on a 75 hertz, so you can calculate the lambda for that frequency. And you are working on a gigahertz regime, you can calculate the lambda for that. So if you want to traverse a length, so how many cycle he has to go? For his case, the lambda is very large for a
right,
gigahertz frequency. So that is for
Yeah.
him,
So
it's not a
so
matter.
yeah, now I understand the question. So the other
yes,
device Shanos was talking about, this PM, that device work at very high frequency, so 42 kilohertz. And in my other measurement, I should measure the signal at F and 2F. So I have to measure the signal at 84 kilohertz. Then there the length of the BNC cable, those
okay,
things matters.
true, true, okay,
So
right.
how much length you are using, the signal will drop like that. But in this case, it is insignificant.
Yeah, thanks, Divya.
Yeah. Mhm. No, no, if you Mhm. Mhm. Yeah, yeah, yeah. In lock-in also, we can do that. We can do R and phase, but yeah, you can. Yeah, go ahead. Yeah, we do. Not for what I showed you here. So in my other experiment, while I'm doing a magneto-optical Carr effect, there I have to measure the signal at F and the second harmonic 2F. Okay, so and there also, as it's a modulation spectroscopy, so there I do the measurement in XY mode. So basically, I am measuring the relative phase between X and your signal will be and log that and the lock-in internally will set some phase to change to take all the signal from Y to X, and your all signal now on will be on X only. Thanks. Okay, then it's done and I can leave. Yeah.
Yes, so I guess so. One last comment I would like to make is for all of us who are present here is like you can actually like send us your inputs and your analysis about how these talks are going, and if you guys want us to change something or include something, some critical analysis of this venture that we have undertaken. So that would be really nice. That we would really appreciate that. So with that comment, let's end this session for today, and we'll see you next week. Okay. Bye.